I am Frank Konkel, the editor-in-chief here at GovExec. I'm really happy we're here to talk about the final frontier, and I think we're the only really space-focused panel of the day. With me today, I have Dr. Derek Tournear, Director of the Space Development Agency at the Space Force, on our far left. And I have Bill Vass, CTO at Booz Allen Hamilton, in the middle.
Yeah.
So thanks for being here, both of you. We've got a lot to get to. Space, satellites, AI in space,
yes.
Lots of stuff. I do want to get a pulse on the audience, though. Who here has a stronger than medium interest in the topic of space right now? Who here would take a free ride to space a la Katy Perry on Blue Origin if it was offered to you tomorrow? All right, I was pretty like third-ish or so.
I've done the Vomit Comet. That's the zero-G flight. That's good. At least it gives you the feel of it.
Before we get into some action news, on the order of 10th anniversary business, I just heard that Katy Perry and Orlando Bloom broke up. I got a news alert this morning. 10 years they've been dating. 10 years we've been doing this event. They don't exist, but Defense One texts them it does.
There you go.
So we're still here. Derek, I want to start with you because you guys had some really interesting news this Monday.
We did.
Let's talk about it. It's really important for what you're doing.
We did. So this Monday, as part of the SpaceX Transporter launch, so the SpaceX Transporter, for those of you that are unaware of this program, it's a program that really enables a lot of technology and a lot of industry. It's a program that SpaceX does every 6 months where they launch ride shares from anyone that wants to go on it and go. And we at SDA have launched several missions on transporter missions in the past. This last Monday was our most recent one. It's called our Dragoon mission. So Dragoon is the first of our TIDES demonstration missions. So TIDES is our Tranche 1. We have spirals of technology that we deploy for warfighter capability. We call those tranches. Tranche 1 is the first operational one. TIDES is the Tranche 1 demonstration and experimentation satellite. So these are all demos. Dragoon is the first one of the demos, and it has two primary missions. The first and foremost was to demonstrate the York satellite bus that will be flown on the Tranche 1 transport missions launching later this summer, just to demonstrate that design works and it works well. And that was actually part of some of it internal reviews that people were looking at SDA and they were saying, you guys are doing great work, but you really need to make sure that you burn down some of your tech risks before you do your large tranches. We said, that's a good idea. So that was one of the things we did on Dragoon. We flew that to demonstrate it, and it's working exceptionally well so far. It just launched on Monday. The second main point of Dragoon was to demonstrate to be the pathfinder for our Tranche 2 beta mission, which is a communication mission that is tactical SATCOM. So it's UHF and S-band directly down to special radios down in the theater for the warfighters to use. And so the payload that is flown on Dragoon now will be demonstrating that capability for Tranche 2. And so that's the important thing. So the beauty of this model is we do a demonstration. That's why we call it the Tranche 1 demonstration experimentation satellites, and that technology will feed directly into Tranche 2, and that's how we continue to do the spiral. So that's all working well. In fact, I want to have some late breaking news on Dragoon. So Dragoon, we have that satellite is full in what we call operate mode. So when you launch a satellite, you first start off in kind of a safe mode because you never know how long it's going to take to get contact with it, make sure everything works out and gets working. And then you go through a long series of test and checkout before you declare it to be in operate mode. That satellite is now in operate mode. What is today? Today's Thursday. It launched on Monday. Just to give you guys an idea, and this is why I'm such a believer in this spiral development model where you launch, learn while you're building the next ones, and you just continue to do that spiral development. On Tranche 0, it took us approximately 4 months from launching the first satellite to where we were able to say we're now in operate mode for that satellite. And so that's kind of the learning curve we're talking about here. We went from 4 months to less than 4 days. And so that's this whole model, and that's what we keep pushing. So I'm excited to see it up there, excited to see it working, and even more excited to see Tranche 1 launching later this summer.
What are some lessons learned from Tranche 0 as you've gone through this? And you have been able to not only speed up launches, but speed up contracting and acquisition, which is no small feat itself. And I know you have some numbers around that.
Sure. So our on Tranche 0, our order to orbit was 27 months for the fastest, and then the longest was around 40 months. So that's kind of the benchmark that we use. And to put that in historical perspectives, that number typically for traditional DoD acquisition systems is closer to 8 years. So we were able to really beat that down, and that's the cycle that we want to continue. We want to continue what we have as 2-year centers from one tranche to the next. So Tranche 0 first launched in April of 2023. We didn't quite hit the 2 years because it's past April of 2025, but we're close, right? So we're coming up close to that. You know, if we're not hitting 2-year centers, we're hitting 30-month centers. Well, you know, that's close enough for government work. We'll continue to work on that and try to get it down to the 2-year centers if we're at 30-month centers now. But that's kind of what we're driving at. So that's one metric. The other metric is just in the acquisition process itself. And this is, you know, for folks that are actually building satellites, folks that are in industry that are working on these programs, it seems absurd that, you know, on some government programs, it takes as long to get a proposal in and write a contract on that proposal as it takes to actually build the hardware. But historically, that's kind of been the case, and there's a lot of reasons why. You know, there's just a lot of reasons why. What we have done, we've demonstrated that we go from solicitation, so we put a solicitation out on the street, said, industry, we want this capability, to writing a contract. That's about 110 days is our average, and that's what we want to continue to push for. Our metric is get that as close to 100 days as possible. We're just over that. We're continuing to push on that. Those are the kind of metrics, and to put that in perspective, that can easily be a year for a lot of these government contracts from the solicitation to the actual contract award.
Those are real. I mean, that is indication that things are working and could even work better, but that's really good progress so far. Bill, let's go over to you. Mm-hmm. Talk to me about Booz, the sort of nexus of emerging technology and space and what you guys are focused on. You guys have a long track record in this stuff as well, in this arena, GPS satellites, among others that you operate. Talk to me.
It's true, and we just recently launched on the Axis mission as well, the Aura Ring for the astronauts to do better space sleep studies. Just recently put with Meta the large language model in space for Llama right on the International Space Station so that they can do better diagnostics in real time and have a chatbot that reacts immediately there that they can operate with. We have a lot of commercial partners we work with. For example, there's Starfish, the Otter launch, which is pretty cool too. That is a system that can grab other satellites and pull them into higher orbit. So it does intersects all autonomously with edge processing in space. And then on the reconnaissance side, we just did work with Albedo, which is a ultra low LEO orbit, just almost bouncing off the atmosphere LEO. And so we do a lot of those kinds of things.
My ears perked up when you said AI in space, around Space Llama. Mm-hmm. So that's a large language model that's actually operating
on the space station.
Talk about that. Large language models are everywhere. We saw a panel with Katrina at OpenAI earlier today, the panel that with Jason just before this was starting to get into that realm. But that's how fast AI is changing. I don't think we were really having these conversations 2 years ago. Yeah. And now we're in this agentic large language model timeline, I guess. Yeah,
well, I think you're seeing it as the previous speaker talked about, autonomous systems all becoming software-defined. Satellites are all becoming software-defined. And you're getting more and more processing capability on the satellites. And when you do autonomy in space, like you're doing swarming and coordination or disaggregated processing, you need to do the ML in space. The machine learning has to react there in space. So you do training, say on Omniverse, which is one of our partners with NVIDIA, and you do the training in the cloud, for example, on AWS or something like that, with massive simulations, right, along with real data and synthetic data, and then you push the inference model onto the satellites. So you do need GPUs on the satellites, and I think you're going to see a lot more. You may have just seen like the Chinese just launched their first of 2,800 satellites that have processing in space, and they predict that they're going to have 2 petaflops of processing in space, which should worry us a little bit.
Yeah,
With the ability to do a lot of that large language model processing in space and tipping Q immediately in space, along with disaggregated processing, and it's going to be a compute and storage race, and along with everything else in space.
How do you determine when you need to have processing power in space versus on the ground? I mean, I'd love both your guys' opinions on that.
Yeah. So when I was at AWS, I worked a lot with NASA, and we did the simulations for the Mars rover. So one of the things I'm really proud of, that's the furthest any of the software I worked on ever has been.
That's pretty cool.
Mars. And you have to, it's 20 minutes, like 2 things I've been dealing with my whole life that are pain in the butt. The speed of light is just too slow, right? And force equals ma, right? Those are like the realities we have to deal with, right? And so it's a 20-minute one-way, 20-minute back to Mars. And so you have to process the autonomy on the rover. And it's the same thing, if you're in a high orbit, you're talking about 750 milliseconds each way, something like that. And so you need to do that autonomy on the vehicle. A certain amount has to happen on the vehicle. And you can still do a lot on the ground. If you're in LEO, you've got, 30 milliseconds-ish. But as you start getting into the second range and things like that, you'd have to do more and more on the edge. And so we have a whole edge system that we load on satellites and drones and autonomous vehicles and things like that, that we're kind of making to operate everywhere. But but it's a balance, right? Because you only have so much space wattage and power on the satellite. That's another limiting factor. You have weight. That's another limiting factor. And especially if you're going to move the satellite, that's where that stupid F equal ma stuff gets in the way. So
you're the first panelist I've had call out 2 scientific equations as problems.
Yeah, they are. They are. Yeah. The speed of light we think of it as very fast, but compared to the universe, it's quite slow.
Yeah.
So, one of the things I want to commit to after hearing the previous panel talk about autonomy and autonomous vehicles, we are going to make sure that all the Space Development Agency satellites are unmanned. Just forget that. And I decided at that point that we're not going to put people on our satellites going forward. That's a joke there. All right. So, it's funny because it's one of the things that we've thought about for a long time. And actually, from SDA's perspective, one of the things we looked at was, okay, how does the UAS community solve a lot of these problems? Because a lot of that, there's been a lot of work done on autonomy for UAS systems because the environment is a lot more dynamic than it is in space. So space has historically been flown where you have satellites, you have communication, you send up commands, those commands operate autonomously, but realistically, they're just following a set of commands. And then if there's a problem with that set of commands, you go into a fault mode. And then the next time you get communication with that satellite, it said, hey, there was a problem. You spend a day trying to figure out what that problem is. You upload a new set of commands. That's autonomous, but it's not really, right? It's just executing a procedure. The UAS community can't operate like that. The UAS community, while a lot of times they do have direct comm, beyond line of sight comm, they can do remote piloted vehicles, the vehicle itself has to have a lot of ability to do its own corrections and be able to handle a dynamic environment and do that without reporting back home and still do it in a safe manner. And so one of the things we did, that's why we at Space Development Agency originally went to University of North Dakota. They have a lot of work in autonomy on UAS systems. And we teamed with them. Now we have an ops center at Grand Forks Air Force Base up there, and we're teamed with University of North Dakota to work on that stuff because we wanted to make sure we pulled in all of that technology and work and just the thought process on doing autonomy on the UAS systems into the space realm, because you need to get out of that mindset that you're just following a set of procedures, and you need to get into that mindset of how do you actually make real-time decisions on orbit. And you start small, you start simply. You hear a lot about autonomous rendezvous proximity ops, where you do that by centroiding on an image and being able to go in and move out. It's still, there's some autonomy there, and there is some amount of machine learning, but most of that is very scripted and is still very procedural. As you develop those techniques and procedures, that's going to get more along the lines of true AI. And so what does that look like from SDA's perspective? So we're going to fly hundreds of satellites that are all connected optically with laser crosslinks. So we'll have, near instantaneous. There's the speed of light in there, but it's for
high
our
bandwidth.
High bandwidth, and for our distances is near instantaneous communication amongst them. So what that enables us to do is it enables us to put processors on all of our transport layer satellites. So those are our communication backbone satellites. We have a battle management command and control processor on board. It's a very sophisticated processor with a lot of compute activity and capabilities. And we can essentially then treat our entire transport layer as a federated cloud computer in space. And so we can do computations across that. What do we want to do? Well, the key thing we want to do with that is we want to be able to have this network actually heal itself autonomously. So that's a crawl, walk, run. We're going to start with a process where we have a managed network, an IP-based network, where we have MPLS data that we upload files and do all of that network management on the ground. That's how we start. But ideally, you want to have all that processing and capability done on orbit so that if there are nodes that go on or off, it's a lot easier for the network to heal itself autonomously without having that ground communication. Again, for speed and resiliency, so you can make sure you provide those capabilities to the warfighter. So that's number one. And then number two, you want to also be able to fuse data on board without bringing all of that data down to the ground. There's a lot of advantages to that. Number one is speed, obviously, and number two is just bandwidth. If I have all of this laser communication on orbit, I can do a lot more processing on orbit. Whereas if I wanted to go down to the ground, I may have to dumb down some of that data because I can't send it all down to the ground, do the processing, and send it back up. But on board, I can do that. So that's one of the things. I want to be able to take data from one of our tracking satellites, or that's our missile tracking satellite. A tracking satellite can form a two-dimensional track of a missile. I want to be able to use another tracking satellite to form another two-dimensional track of that same missile and send those to one of these processors on this space battle cloud in our federated network on transport layer to calculate a three-dimensional picture and then send that track directly down, to someone that could take action without ever having to do that processing on the ground. That's where you get into this kind of autonomy where you have machine learning and some AI capabilities involved. So that's where we want to get eventually, and we're pushing for that. We'll start with doing all of that on the ground. You'll hear a lot of people that push back, and you had a good point on the size, weight, and power is a big constraint. If you drive around the countryside, you're going to see these huge data centers, and they're very close to power lines, and they take a lot of power, they take a lot of cooling, and it's a big deal. And you say, how are you going to put that onto a satellite that's a few hundred kilograms that's working off of solar panels? It's true. You're not going to do that. You're going to get there. You're going to get that piecewise, right? You don't eat the elephant all in one bite. And if you look at what's in your cell phone, the compute power that's in your cell phone 20 years ago, imagine the amount of size, weight, and power that was required to give you that same compute power. And that's what we're capitalizing off of to be able to bring this to bear in space. We start mundane. I'll point this out. So, the first thing you want to do if you want to use AI, you start to use things like ChatGPT. We actually have used AI to write some of our solicitations. You'll see there's credit given in some of our requests for proposals that went out that says, we've used some different AI machines to help write some of this. So you start with that. And then we also have, obviously, performers doing the real work on how do you make this work autonomously in space. But we use it across the board.
That's not the secret to your faster acquisitions, is it?
Hey, it helps. It certainly helps because there's so much stuff that's just rote that's in there. And we at Space Development Agency are an extremely lean organization. And so we're always looking for ways that we can continue to stay lean and fast. And that's one way. It helps.
Yeah, and we have a system we use internally at Booz Allen called Propster that automatically writes the response.
There you go.
So maybe we can just not have to do anything, just have them talk directly with each other.
That's right.
Bill, Propster, you said?
It's called Propster internally. Yeah.
No kidding.
Yeah, it's an internal product, but it's one of those things that we do. We can take in a proposal and then analyze it and then build an initial response, and then you give it to people to correct it, and you want to manage it all with people still. But it certainly saves a lot of time on a number of things.
Well, Bill, in the tech projects that you're involved in, is AI not a must-have, or is it a?
Oh, it's in everything. So we have about 3,200 AI professionals at Booz Allen and growing. We build it into everything we use, for software development. We use it for the entire life cycle, from requirements definition to actually writing the code, where, again, people are interacting with it the whole time, to traceability matrix for the requirements and coverage for testing, all the way through to pipeline and deployment and operations. So it's pretty much across the board. And then certainly on all the autonomous systems we're working on, we have partners like Shield AI, where we're taking their platforms and extending it to work on an F-16 or a satellite or other things like that, or Scout AI, who's working on new large language models to do autonomy as well. So I think it's going to just be embedded in everything. It's here to stay. But remember, you're really dealing with a 3-computer problem, right? You've got in the simulation world, you need a system that can run the simulation, like an L40S on NVIDIA on an AWS cloud or something like that, running Omniverse, and you're using real and synthetic data there. And then you've got the, say, H200, which is the machine that is learning. That's where the model's running, and a cluster of those. And then that builds an inference model, which is the 3rd computer, which is the smaller, lightweight computer that's in the car on the satellite. But I think, as you get more and more of this disaggregated compute in space, the commercial providers are putting that up there. You've got, OneWeb, you've got Kuiper, you've got SpaceX, obviously, and Iridium's still there as well for lower bandwidth omnidirectional processing. You'll be able to laser link right into if you need to burst from a defense system cloud in space to a commercial system cloud in space, you'll be able to laser link to those comm satellites and do that. The other thing that's very exciting about compute in space to me is you can have really dumb, cheap sensors on the ground. And you can have just a camera on the ground that's $20 with a little phased array antenna and a solar panel, and it can have all the power of a huge large language model by connecting into space. So I think that's going to change the way sensors work. I think these cheap drones you're going to see more and more have this full capability. Basically, their brain is extended either through the satellite back to a cloud data center or right to the satellite, depending upon the latency requirements. So.
I want to add to that a little bit, because it's really interesting that you say that. A lot of these UAS systems or unattended ground systems or anything tie into space, and it makes it a bigger ecosystem.
Yeah.
It's funny because when we within the Department of Defense started pushing this whole concept of proliferated LEO, one of the areas where we got a lot of pushback, there was a lot of pushback from the UAS community itself, and they said, "What are you trying to do? Are you trying to completely supplant the UAS community from space and do all of these UAS missions from space?" And I had to push back and say, no, that's not what we're doing. There's obviously missions that are better suited in space and on the UAS. But then I started to think about that, and there's an analogy that I give people that I think will help set the UAS community at ease. In the 90s, there was this big push to go to all digital offices, right? We were not going to have paper anymore. There was not going to be any paper in your office.
I remember that.
All digital, right? And we use more paper now than ever. And why? Because it's just so easy to hit Control-P and have it print out. And so what actually happened when you connected all of these computers together in a network system and you had all this processing, it just made it so much easier to use the tools that you were already used to using, right? You were already used to reading and seeing things on paper. And I see that's the same thing with the UAS and space community. And especially as they get more of this autonomy and more of this, artificial intelligence tying them together. The space layers that are giving you this ubiquitous comm and more processing capability are just going to enable all of these other missions, especially in unattended systems like that. So I think there's going to be just a rapid growth in both space, and that will be enabling all of these other activities.
And I think you're going to see this on the commercial side. When I was at Amazon Web Services, I did all the connected car work and autonomy and training for that. And you're seeing more and more of this idea with there's 125 processors in a car. But you build a car and it runs for 25 years, software gets bigger and bigger, won't fit on the older cars. So they have this concept where they're offloading some of the processing to the 5G nodes and to the satellites. Right, and that will let the older cars be as smart as the newer cars. But that's where they really have to decide on latency. You can't put the ADAS system on a satellite, right? You can't put the ABS system on a satellite. But your IVI system, your nav system, the video games in the
Right.
car for the kids in the back, you can put that on a satellite. So you can start offloading those things to make more room. And I think you're going to see that sort of dynamic environment where everything has a split brain between the communications 5G nodes and when they can't get that between commercial satellites. And then, of course, that enables the battle space as well, right?
Yeah, that's
You can also have those split planes. So I think you're going to see this across everything. Part of what we do at Booz Allen is we have this Edge Extend product that allows you to dynamically sense where you are. And we actually put some AWS APIs in space and on drones and in the car. And so you can write the same code, run it in the cloud, constrained in the cloud, simulated in the cloud, and then push it to the device, which I think is going to continue to accelerate things.
Bill, going back to something you said, and I'm sort of formulating a question as we're talking, but pretend I'm a big, dumb ground sensor.
Okay.
Right? Explain to me how complex these challenges are when we talk about AI actually in space.
Yeah, we'll do a really simple example on your dumb ground sensor. You're a camera, and you're running a product called Kinesis, which is something that I worked on at AWS, which is streaming the video. So it streams any frame series time data very easily into the cloud. And you don't really want to send 30 frames per second of an empty parking lot all day long, right? What you want to do is at 2 o'clock in the morning when a car drives through the parking lot, you send that. The rest you don't send. So you need to have an ML model that recognizes the car. Okay, if you don't have enough processing on the camera to do that, you could have that ML model on the satellite, right? And then it could do the tipping and queuing and filtering. I mean, it's just like one of the first missions I worked on in putting ML in space. We put this little at Amazon, this little thing called a snow cone, which is a ruggedized cloud server that's about this big on the International Space Station. And all it did basically was take ground imaging and say, this doesn't have anything worth sending in it, right? It's just clouds, right? Throw it away. Or it's empty ocean, throw it away. Oh, if ocean with ships, keep it, right? And then that reduced a significant amount of the transponder requirements for the satellites. It also did some other things of filtering video inside the space station as well.
Pivot away from space for 2 minutes. I'm curious, you mentioned there was 3,200 AI professionals at Booz, right? How is this era that we're in changing the type of people you try to bring into the company, the type of people you want engaged with public sector? And then same question for you, Derek, on the kinds of people you seek coming into SDA.
Yeah. I think you're getting to a point where you want to have good AI practitioners who understand the limitations and understand also what it does effectively, where it's good and where it's bad, right? And I think that's going to continue to evolve. You want people that are not afraid to use it. I always tell people that you should start off assuming it will work, and then what is it? Trust and verify, right? Assume it will work, but verify it all the time. And so you want to be managing it, and so you don't want to be afraid of it. It's interesting to me. Like my daughter's a software engineer, works at a startup. Actually, she does satellite intersect controls for a startup. Managing satellite processing, and I keep trying to get her to use Cursor, and she doesn't want to use it, which is interesting to me, whereas a lot of my developers just love using Cursor, right? Or, Copilot or, Klein, or like there's a number of them that we're using. But I think there's some resistance for some people. Her opinion is, well, gee, I'll just have to check everything it does. It'll take me longer. I might as well just write it. But these tools can really do the boring stuff for you. I mean, it's sort of like, when we at Amazon, I think we managed when I was there about 750,000 robots in the fulfillment centers. I think they're up to 1 million now. And the robots do the dull, dirty, and dangerous work. And so I think these AIs in coding are going to do the dull programming for you, and that let you be much more creative. So we really look for people who are going to be very creative and are not afraid to use the tools.
So from my perspective, in the government, typically people have a career in the government and they grow up in an acquisition profession. They learn a lot about acquisition, and they learn about watching performers do work and kind of reporting on that and seeing on it. At SDA, what we really need, we have a growing need to be able to have people that really know how to do the engineering aspects of what we're asking the performers to do, so they can come into SDA and we can really have a better teamwork with the industry performers. And so what's that look like in particular? So some of the lessons learned we had on Tranche 1, and we're seeing it a little bit on Tranche 2, and we're fixing it on Tranche 3 and beyond, is we, at the government, I was always taught in the government, the government doesn't want to be the integrator. The government is not good at integration. You want to be able to manage programs. You want to be able to have someone in industry integrate. Well, what we're doing at SDA is we are following, I always liken it to the Android model, where we have full and open competition. We have multiple vendors on each tranche delivering each different individual capability, and we have them plugging together into a unified architecture with verified ICDs, interface control documents, and standards that we have test beds set up to make sure that they match. There is a lot that is inherent to doing integration to just make sure those pieces and parts work. And it is very difficult. It's actually more difficult to hire someone to make sure that that is managed properly than it is to build up that experience base and expertise in-house and be able to do that. So I've shifted to say that the government actually needs more expertise to be the integrator. Back in the way that the government kind of used to do that, it got away from it. I think we need to get back into that. And so what that looks like, where you get that expertise, you don't get that expertise inside the government. So what we look at SDA is we want engineers and program managers from industry to come into SDA, and we actually like the whole revolving door concept. Go into industry, learn these real skills on how to actually build and test things, come to the government to help to do the integration and help to tie all that together. And then if you want to go back to industry, that's fine. We prefer this kind of revolving door because that's the kind of expertise we need. Yeah. Obviously, there are core competencies in the government that you need with contracting and those kind of aspects. But the ability to pull folks that have learned the capabilities and the skill sets as actual industry engineers, pull those in to have them actually manage and oversee projects and help do that integration is key. So that's one of the things that you'll always hear us push. And most of the senior leadership at SDA now has come from industry. And you know, we're in government now, but has served time in industry. Our chief engineer has spent a career actually building satellites and then come in and is helping us. So that's where I would say is the shift within SDA in particular, but I think you'll see that across government as well in different acquisition organizations.
Yeah.
Bill, go ahead.
Yeah, I definitely agree with that. As someone I was an SCS at the Pentagon and also been in commercial, I think it's great for people to go back. I think I wish a lot more people went into the government for periods of time and also did commercial industry. I think it's really important.
Speaking of the Pentagon, one of the big initiatives they have going on is Golden Dome. So talk to me about where Booz fits into all this. And the previous panel talked about swarming satellites as well, and I think you guys are involved here.
Yeah. So we're working on a technology called Brilliant Swarms, which does a lot of what we're talking about. Is this aggregated tracking and intercept in space, and it requires a lot of ML on the satellite, along with sensors, components, and things like that. And it's going to be part, we hope, of an integrated, complete system. The ground-based interceptors, the tracking systems, the satellite systems, and I think we're in an era now where you can put up lots of cheap satellites, right? And so you can get a lot of coverage in space, both for tracking but also for intercept. So I think it's going to be transformational. But those really do work in a shared mind. They really do work with a lot of GPU horsepower on the satellite, and you're making those decisions in real time on the satellites, in addition to communication to the ground. So it's I think one of the big advantages we have is we really understand the whole mission and battle space area. So knowing when to tip and cue and when to react and when not to.
There must be a smorgasbord of companies that are trying to come to you, companies like you, and try to figure out how they can piece and fit into that. I mean, what's that dynamic like? This administration has been really emphasizing speed, and I think a preference to look at non-traditional companies or companies that haven't always done business with government and give them a shot.
It's true, and we're partnering with a lot of them. So I think that's some of the ones I mentioned earlier, as far as the technology goes, all of the different satellite providers and startups that have been launching things into space and operating with them as well. They all, just have aggregates of technology that we can leverage.
Eric, SDA's role in the Golden Dome or the future Golden Dome?
It is really exciting times now, right? I mean, the whole idea behind Golden Dome has invigorated industry. It's got the Department of Defense to focus. I think that with General Gutlein nominated to run that, I think he'll do an excellent job to be able to keep people focused and deliver on this. From SDA's perspective, SDA from day one has been committed to two main capabilities. Number one, beyond line of sight targeting for basically any range of targets. Air, maritime, ground, detect them, track them, calculate a firing solution, and send that down to the warfighter, and do that as rapidly as possible, ideally doing it all from space. That's capability number one. Capability number two was same thing, except now look at the advanced missiles. So as missile technology advances, as missiles become more maneuverable, they become dimmer, detect them, track them, calculate a firing solution, and send that directly down to an effector, and do that all from space in real time. So it's clear those are the two capabilities that are needed to do any kind of Golden Dome mission. So SDA has been developing the technology and fielding these capabilities since 2019, focused on those. So what Golden Dome looks like and such, we'll hear, as the department really finalizes that, and General Gutlein, when he is confirmed and puts together this plan, then we'll be able to speak a lot more about details about how this all comes together. But for now, I'd say I am confident that the technologies and the missions that SDA has been developing and delivering will certainly be enablers for any Golden Dome mission.
Right. We've got about 10 minutes left, and this is like a large, curious audience, so I want to give a chance to ask some questions. We have some mics in the back and a couple questions down here in the front. Let's start in the front, because they're, based on the speed of light, I saw them first. So let's, Amber and Green, and then Sydney over here.
Hi, I'm Amber Corin, freelancing for GovExec today. So looking at this kind of broader program, TIDES, the broader proliferated warfighter space architecture, which I know you didn't get to touch on very much today, I'm curious about how these fit with kind of like the established constellations the government already has in place, albeit in different orbits, WGS and GEO, focused on warfighter comms, ostensibly the forthcoming Space Systems Command MEO constellation focused on missile tracking and warning. How will will they fit together? Will they complement each other, augment each other? How do you see all of that coming together?
Sure, no, thank you for that question. And Frank, I don't know how you're seeing this here. You must have a phased array in your eye to block out the lights, but it's a good question. So they're complementary, first and foremost. So the main things to keep in mind are the focus of SDA's capabilities are to start with the warfighter and then kind of work up from there. And so what I mean by that is our transport layer, our communication layer, is focused on delivering tactical communication down to Link 16 radios. Why is that important? Well, there's already over 10,000 Link 16 radios fielded, operated. Our warfighters are training with that. They have that in their techniques and procedures, and so they're already using that. So that's kind of a mission set that was not being fulfilled by traditional large Department of Defense communication messages. It wasn't going down to the tactical user using radios they already had fielded. So we kind of filled that. So that's complementary to more of the backhaul type missions that WGS and others perform. In addition to that, a lot of those missions, especially when you talk about the integrated broadcast system over UHF that are coming down off of geosynchronous birds. So space is now a contested domain. And one of the ways that you can assure that you can provide that capability to the warfighter is to proliferate so that you can be more resilient. Yes, you can shoot down a low Earth orbiting satellite just as easily as you can a high geosynchronous satellite, but you have to shoot down a lot of them, and it takes a long time. And so your service gradually degrades under attack. Whereas in GEO, if you take out a 1 to 2 satellites, you can have a large degradation in service immediately. And so it gives you that resiliency. So that's again where they're complementary. And that's more on the communication side. And then we have our tactical comm that's being demonstrated now on Dragoon and is going to start on Tranche 2 beta. That's a completely new mission that is not being fulfilled before. So that's complementing some of this tactical SATCOM from space that traditionally was not done from space. On the tracking side, That is, it is actually a very well orchestrated and beautiful force design that ties them all together. What SDA is doing with PWSA with the tracking satellites in LEO, what Space Systems Command is doing with the tracking satellites in MEO, and we're working very closely with the Missile Defense Agency to tie all those together, and how that correlates with the legacy systems that are at GEO and at highly elliptical orbits. Essentially, what the LEO and MEO constellation give you is, again, more resiliency. So if you start to attack, and you'll use different vectors to attack a LEO satellite versus a MEO satellite, you can take one out or the other. If you take one out or the other, you'll essentially provide holes that kind of self-heal over time because the orbits have different periodicities. If you then want to take out a complete capability to completely blind us for missile warning, missile tracking, it is a much larger campaign to be able to go after both the LEO and MEO satellites. So it adds that level of resiliency. The LEO satellites also, by virtue of being closer, give you more capabilities for the missile defense actual mission. So you can actually see more targets than you can higher up, and you can actually give better fire control quality on those targets. And that's a continuation of what MDA demonstrated with their HBTSS program. So from LEO, you get missile warning, missile tracking, and missile defense. From MEO, you get missile warning and missile tracking. And then from the GEO and higher orbits, you get the missile warning. And then with the three of those all together, you get just an incredible amount of resiliency, so you can provide that capacity and capability to the warfighter. So I hope that answers your question.
Sydney, right here in the front, had a question as well. Mike's right behind
Seriously, how do you see that?
I got good vision.
I'm maybe hard to see, but I am very loud.
Okay.
Sidney Friedberg, Breaking Defense. For you, Director, I wanted to ask, we've talked about getting various levels of autonomy actually on orbit, from sort of the old school if, then, else. You give it a list of instructions, it follows them mindlessly. If it doesn't work, we'll try again tomorrow, all the way, might have some hypothetical future thing that's highly autonomous. Where are we actually now in that progression? How much autonomy are we actually able to put on things like the current TIDES demonstrator, for example? And where do we want to get at what pace? And conversely, are there places where we don't want to get, where we don't want to, say, build Skynet and have a completely autonomous satellite that controls all our nukes? Probably that's not in keeping with DoD policy.
Right. So what we've demonstrated to date, so we actually demonstrated on a transporter launch early on in SDA's history. We had a mission called POET that we were teamed with DARPA and others on, and that demonstrated a level of autonomy to be able to autonomously tip and cue different satellites from different phenomenologies. So you would take a radio frequency cue and autonomously tip another satellite to take an image of that, and that was more than just a set of procedural if then else statements. There was a lot of autonomy built into that to be able to learn on orbit what the targets actually looked like that you were interested in, and be able to subtract background as it learned. It did its own machine learning on orbit to be able to fit that out, and then how to do some network management, very limited, but some network management to control that among different satellites. That was demonstrated on POET. So that was kind of the state of the art of what we demonstrated. Where we are on the Tranche 0 satellites, we don't have the battle management control processors in, so it's all, that's all scripted, old school, procedural. Tranche 1 will have the battle management command and control processors on that have that capability for that level of autonomy. Those will be built onto our transport satellites and delivered and flown on those. I don't anticipate out of the gate that we start to use that, but we have that capability on orbit. We've got an app factory. SAIC is actually on contract to build that, and so we have other folks that are on contract to actually build apps on that app factory and test those out, so we can use that as a means to upload battle management command and control processor applications onto that and be able to do that. So you'll see, we'll launch the satellites later this year. We'll get them operational in a crawl phase, and where they're operating in just a single plane, everything else is tied on the ground, to a walk phase where it's operating as a complete constellation, but still all the network management is done on the ground manually, to then run, that's where we actually have these running on those BMC cube processors autonomously on orbit. I would not anticipate that happening earlier than 27 when we get all that ironed out and running. But that's what we want to do as part of Tranche 1. And then as Tranche 2, those apps will be able to run and we'll be able to shorten that timeline. Those are the kind of apps we're looking at, though. How do you do automated network management? How do you do automated data fusion? How do you do automated data dissemination? That kind of thing.
Any other?
Yes.
One question in the
Thank
back,
you.
and it's got to be a quick one because I got
Yes,
about
quick one.
a
About
minute,
the
maybe two if I
Golden
stretch.
Munzer Sulaiman with Al Mayadeen Network. I want to ask about the Golden Dome. Now, with the experience of the 12 days war between Iran and Israel, there was some ballistic missile that they were able to hit their target or whatever. Now, with the Golden Dome, what guaranteed that we can have that it's going to be absolute defense, taking into consideration that experience? At the same time, is this going to create kind of competition in space between the competitor of the United States, like China, Russia, and going to create weaponization of the space? And what is the current competition out there? There's any weapon-based in space to anyone in the world right now?
Thank you.
I'm
Thank
gonna
you for
let
the question.
I was going to apologize. I'm not going to touch that one.
Yeah.
So, I mean, it's, the technology baseline as far as the requirements and stuff is all still being developed. We'll let when the Golden Dome program office is up and running, I think that's a better place for them to be able to address some of those issues.
Thank you for the questions, and thank you guys. I mean,
it was fun.
appreciate your time, and give them a round of applause as we hop off the stage.